Hi everybody, I'm Eran. Thanks for the organizers for inviting me. It's a great pleasure to be here. I'm coming from Israel. I live in Israel all my life. I'm a software engineer. I started to work back in 2005 for SAP and been there for quite a while. And since then, I'm with Google. So this is what I believe. I think regardless of anything else I'm going to say in this presentation, testing is really, really, really important. I hope you're with me on that. And no matter what I do, I always advocate testing as part of development workflow. And hopefully I can give you a glimpse into my world and how we do stuff at Google from this perspective. I'm not going to talk a lot about, or I'm not going to talk about Selenium or WebDriver at all, so sorry for this disappointment, but I'm going to talk about testing in general and especially integration testing. What I'd like to walk you through today is first to give you a little more context from a developer point of view. How does working in Google feel like internally, and why do we care about testing so much? And if you are following the Google testing blog or something similar, you must know that we really care about testing in Google. Then I'm going to talk about the terminology. How do we talk about test? How do we think about test? And I'm going to talk about who heard the term flaky test? Who never heard the term flaky test in his life? Who heard? Great. Okay, so we'll go through the formal definition anyway, don't worry. And we're going to talk about deflaking strategies. Okay. So welcome to Google. I'm going to talk about our code base, and I'm going to present statistic from 2015. It was January 2015, so it's 2 years ago. I was too lazy to find new statistic that I'm allowed to show you, so this goes back 2 years ago. And please consider that everything in the digital world grows exponentially, right? So whatever number I'm going to show, we have much more of this today. So in our code repository, we have this number of file, 1 billion file. It's a pretty big number. We have 9 million source file, which source file is like code source file written by humans. Okay, all the rest can be stuff like generated file, compilation artifact, test data, binaries, images, configuration, whatever. But we have 9 million real files that are running and people modify on a daily basis. We have, what is that, 2 billion lines of code. It means that we have, on average, a little more than 200 lines of code for each source file. And our history, like revision history, goes 35 million commits back. It means that we keep revision history for each of the files since more or less 2002 or 2003. So if I'm browsing into the source control in Google and open a file that was written originally back in 2002, I can go back, see any revision that took place since then, any comment that was given by the reviewer, any response that was handled by the original author. I can see the change, and the history goes very deep, and we keep track of all of that. There are 45,000 commits per day for the source control, and there are 15 million lines of code in 250K file changes per week by human. This is a lot of code that we change every week. Just to give you a sense of perspective, this is the same number of lines of code as in the Linux kernel project. So it's like, if you want to think about it, Google changes code in the scale of the Linux kernel every week. And it gets pretty complex. So, by the way, I say human changes. So 2/3 of the code is being changed by robots in Google. Robots do a lot for us. I hope for you too, right? They generated stuff. They compile stuff. They do much of the boilerplate for us. And generally the approach is to give to robot to do whatever he can and save you the time. After all, this is test automation conference, so I hope you have this state of mind as well. Our source control serves 800,000 read requests per second at a daily peak. This is quite a lot. And why I tell you all of this? Why I'm sharing all these numbers? I'm sharing all these numbers to say that it's not only the fact that we have huge source code. Most engineers in Google, regardless of what project they're working on, whether they're working on Gmail, Google Maps, search, anything else, self-driving cars, they are walking through the same version control. Okay, we have one huge repository that contains all this stuff, and everyone works on the same version control. It means, just for example, that if someone wrote a library 15 years ago in Java that manipulates string or something, everyone uses that, right? We try to don't repeat ourselves too much. And when I build my project, every engineer in Google, when he builds his project, he depends on many of these libraries and actually build them from the version control. Now, let's walk through a very simple example. Let's say that I'm responsible for the search front end, right, google.com. I'm not, but just an example. So what I want to do is to build a C++ binary. Okay, this is the binary of my front end. The name I want to give it is search front end, and I have a source file for it. But I'm specifying that I have a dependency over a C++ library, which is defined in the search.h header and in the source file. Okay? And this library depends on something else, which is a different library, and so on. So a typical project in Google will depend on an order of tens of thousands of other libraries, and whenever it wants to build them, it will do this. It will compile the whole thing each time. Obviously, we don't do that locally. We do it in a distributed manner, but it doesn't change the fact that each of us depending on all the rest. Now, before I'm going to say that everything is built from head, I'm going to say that usually when you deal with such complex dependencies, you will do some version management, right? Say, I work on a project and we have team A and team B. Team A depends on team B. Then team A would say, hey, we don't want to get your bugs, so go ahead, develop your version. When you have a stable version, give it to us, and we'll take it as a dependency, right? We don't want to take any change. So this is the way it's done mostly, but not in Google. In Google, everything is built from head. Now, what does that mean? That means if I'm team A, and this is team B, and team B just submitted a change, okay, that exposed a new bug that will only be visible in my product, if 1 second later I will invoke a build of my binary, I will bake in the bug into my product, and it will be exposed to the rest of the world when I launch it. So everything is built from head. This is what you should feel about the notion of everything is built from head. Okay, it's a little crazy, but this is a decision that was taken a long time ago in Google to have a single monolithic version control repository. It saves a lot of complexity, by the way, because we don't need to deal with branches. I don't need to think, wait, I need to wrap up the string library from stable, will it work with my new API, so on. No, so everything I built from head. But it must have a hidden assumption that says everything in head should be fairly stable, right? Which means any change that any developer check into the code base of Google should be very well tested and very well thought about. Otherwise, we will deal most of the time with debugging breakages and rolling back changes. So this is why we care a lot about testing, okay? None of this can happen manually. You can't say just, please be responsible, check your changes before you submit. No, that just don't work in such a scale. You have to have a very strong discipline and testing culture. Another risk that we deal with on a daily basis is that so far I talk about build level dependencies, right? Compilation level dependency. I'm using another library, I depend on it, then potentially this library can cause bug in the product I'm working on. But there are also runtime dependencies, right? For example, if my product wants to authenticate a user, I'm not responsible for authentication. Then in runtime, usually I will just send the user credential to another system that will say, hey, this is the user credential. Do you allow this user in or not? Okay, this is an example for runtime dependency. Now, runtime dependency can also break, and it's even more complex than that because every service has a different push schedule, right? So again, we have team A, team B. Team A depends on, I even have a drawing for that. So let's imagine that this is my service. It's an application. Imagine what you want. Let's say it's Gmail for that purpose. And this is the authentication service, right? So every time a user goes into his Gmail, this system will send a request to the authentication service. It all happens in the backend, by the way. It's not something that issues from your browser. And it will say, do you let this user in to this Gmail account? Now, they will push to production whenever they decide to. And we will push to production whenever we'll decide to. I mean, it's not possible to say, hey, let's do 1, 2, 3, and everyone push to production. It doesn't work. It's separate teams. They have separate schedules. So for example, we can decide that we push to production on a daily basis. They do a weekly release, and so on. And obviously, there are version skews. So if a bug is introduced here, and the wrong response returns to here, this will fail at runtime. And by the way, it's dangerous also in this direction. We call it the ray of death. Then if we have a logic bug here that issue 100 requests instead of 1 request, I don't know why, okay? It can DOS this server, right? It can kill it. So these are runtime dependencies, and they're pretty tricky to deal with. Now, this is a Selenium conference, so I want to ask you a related question. What do you call this is the question. What do you call a test that tests your application through its UI? UI test. That's one answer, yeah. End-to-end test, yeah. Don't be shy, come on. Functional test, very good. Sorry? High-risk test. Okay, so I anticipated some of these answers, but the point I'm trying to make is that there are many, many ways that people refer to UI test, integration test, whatever. You know what I'm talking about, right? This is a Selenium conference. And there are many different ways that people refer to to this kind of test. And we think it's a bad thing. We think it's a bad thing that the terminology around this area is actually not so well defined, because if you move to a new company tomorrow, they will refer to testing elsewise than you used to, and it will take you time to understand what they mean when they say unit test or an integration test or a UI level test or a Selenium test or WebDriver test. Is it even Selenium or WebDriver? This is like, according to my understanding, by the way, Selenium 2 is also known as WebDriver, but I don't think that no one in the world knows what the answer to this question. Anyhow, we think that this is important because different tests have different properties, right? Tests can be very different. If you're referring to a small unit test that tests a very basic functionality of your class or your method, and it takes a number of milliseconds, an order of milliseconds to run this test, and it's very fast, it's very reliable, it's very stable, then I'm talking about something completely different than an exhaustive Selenium suite that takes 2 hours to run, fail half of the time. You know what I'm talking about? This is something very different, right? So we need to call this thing differently. Why it is such an important thing, by the way, to distinguish between this type of test? Just think about scheduling. Think about your continuous build system. Hopefully you have a continuous build system, and this continuous build system needs to trigger a test at certain events, right? When you're checking code, you want the system to run tests. Before you're checking code, you may want the system to run tests. Before you cut a release, you want it to run tests. Now, if I'm doing local development in my IDE, I definitely don't want to run the 2-hour suite every time I make a change. But I do want to run the unit test when I do that. So this is scheduling. And it's important to first have the common logic to talk about it, to common language, sorry. So at Google, we tend to make decisions based on data and not on intuition. And therefore, we decided, and I'm sure some of you heard it, to speak about sizes of tests. So over at the time, we started to define a shared terminology that speak about small, medium, and large tests. This is something very stable. We'll go through the definition soon. But basically, it is so well defined that we can write automated tools that take test code as an input and tell you what's the size of this test. So I'm going to talk about small tests, and then I'm going to talk about large tests, and then I will tell you that medium test is something in the middle. It will just save me some explanation. Small tests are what most of us refer to when we say a unit test. They basically test a very specific part of your source code. It can be either a function, a specific path through your function with very well-defined input. It can invoke more than one function, usually in the same class, but not a lot more than that. You can see the visual demonstration to the right. They use specific logic condition, which means the method or the class will be fed with a very specified predefined input. And there is a heavy usage of mock, stubs, and fake in this test. So if my class depends on something, I don't want to involve this real something in my test, right? Because it's just noise. I will mock or stub out the dependency. These tests are really, really fast by definition because they take in a little piece of code, they run through it, and that's it. There is no reason for a small test to take more than a couple of milliseconds. This test has no connectivity to anything, right? I don't want in a unit test to to call a Twitter API and to ask what's the title of the most trending tweet in the last 24 hours, because then this test, by definition, won't be stable, and it won't serve me, right? So there is no connectivity. There is also no sleep statement. In such a test, I won't say sleep for 30 seconds. Personally, I think it's always a bad idea to sleep in tests, but obviously in unit tests, we don't want to wait for something. Everything is run synchronously on a single thread, single process, single machine, and it's just procedural. And these tests are usually the most efficient we have. We run them frequently. We run them as part of the developer workflow. We run them before we check in code into the source control. And actually, we want to run them as frequent as possible whenever I run something. Large tests are the other part of the world. So if we look at this visual demonstration, it's something that tests completely an entire workflow of the application end to end. Many times they are done through the UI, because UI is one end of our application. Not always. Sometimes the service can expose an API and not a UI, right? But usually it will start through the most higher interface of the application and will go through all the layers, usually until the storage layer or so on. So these tests are also very important because they are responsible for the real way the application works. And as we all know, you can test each module of the system independently of the rest, have everything working, but something will screw up when you start look how this piece works together. So these are also important. These tests are really, really slow. Okay, first of all, usually most of the time for this test is not about running the test. It's running the system that you want to test, right? Because I need to set up the front-end server, I need to set up the back-end, I need to clean the database before I start, and so on. So these are heavy, slow tests. These tests do have external dependencies, right? So many times, if I look at this piece, so this is an external dependency, right? It will issue a call to a database, which can be a different process running even on a different machine. And this happens if you work on distributed environment. Obviously, there are multiple threads, multiple process, and sometimes even multiple machine involved in such a thread, which in such a test, which dictates undeterministic behavior. Now, we want to run this test frequent as possible because they tell us what is the true state of the application. For example, we always love to run this test before we push the next candidate to production or something. But as we said earlier, I definitely don't want to run this test every time before I check in. Definitely not when I change my code, because it just takes too much time. And we have the notion of medium test, which lies somewhere in the middle, because we have to have somewhere in the middle. Sometimes you want to. It can be sometimes very strategic to test how 2 modules or 3 modules interact with each other, which will go out of the boundaries of the definition of a small test. But still, it's not a large test because it's not the real workflow. I wouldn't want to involve the entire system. And in this type of test, I would usually say it's important for me to see how the code interacts with the database, but I don't want to pay the cost of having a real database in this test, so I will write some kind of in-memory implementation or a more lightweight implementation of the real database, so I can run it in the test context. Now, if you remember one thing from my slides, I want you to remember this. You should think differently about small tests than you think about large tests. It's the same thing like you think differently about Java and C++. You think differently about UI development, backend development, and data processing. So these are so different, okay, that you shouldn't think about it even together, even though they both call tests. So we have large tests, we have small tests, totally different things. And I know we all are, someone said this morning something about the test pyramid. I know we all are a bit tired of listening about the test pyramid, but I still think it's a very important notion that holds a lot of truth. We should rely as much as possible on small tests. We should have, most of our tests should be as small as possible, but the complete strategy is always a combination of different kind of tests, right? Why? Because each test brings us good stuff and bad stuff, each kind of test. The more we write larger tests, we have more confidence in the real system. We cover a larger scope. But the more we write small tests, we have isolation, we have determinism, we can trust our tests more, we can run them more often. So obviously, if you want to be good, I don't know how to call it with regard to testing, we need all these kinds. Now, two more things I think which is important to mention about how we define test and test requirement in Google. Then regardless of the test size, each test needs to be independent from other tests. And that means you can run your test suite in any order. So if the first test, if you have such a notion of the first test will create a user, and the second test will log into the system with the user that was created in the previous test, then we think it's not so good. Why? Because first of all, it always means you have to run the first test before the second test. And if you have two machines now, you can't parallel that. Second, if the first test will fail, the second test will, by definition, fail as well. So it's one bug, two failures. So we think it's a good definition to say, I want my test to be independent always from the rest. And another thing, which is pretty much related to the last point, but it's a bit different, tests should not have side effects. What this means is that if you run a test that will indirectly or directly write something to the database, make sure to wipe out these records from the database before the test execution done. And if this part is failing, make sure you have a backup strategy for this so that you'll know that the state of the world is the same before your test starts and after your test starts. Think about it like resetting the environment or something like this. These are quite basic things, but I think they, again, hold a lot of truth, and these are important to think about. Okay, so fortunately, we all know what flakiness is, but the definition for flaky test in Google is that a test that exhibits both a passing and a failing result with the same code. With the same code, I mean in the same version. If I take a test from the version control and I pull it in version 100, I run it. We are 15 minutes from the start, or I have 15 minutes more? 15 minutes left, okay, thank you. So the test, this is a test that shows flaky behavior. Now, what are hermetic tests? Hermetic tests are these tests that tend to be non-flaky, But if a test is not hermetic, if a test, like the example we gave about Twitter before, a non-hermetic test will be, by definition, flaky. So beware. Now, flakiness is very important to us at Google. Why? Because, as we mentioned, we rely a lot about tests. Okay, test is a part that we can separate from our day-to-day life and developer workflow. And we found out that about 1.5% of all the tests in our repository are flaky. This is a disaster, right? It's like if I need to check in a change, and in order to check in the change, I need to run 100 tests. Usually the situation is that I need to run 1 million tests or more, but if I need to run 100 tests, I have 15% of flakiness. It means that I have 15% chance of getting results which are not accurate. So this is a real disaster to productivity and efficiency. For example, say that I had no flakes, okay, all tests are 100% stable in the repository, then whenever the system sees that the test changing the status from failed to, from a pass status to a failure status, it can actually automatically find the root cause. It could have automatically find the root cause, saying, okay, if the test was passed up to here and it started failing here, then let's see what went in between. We'll do a binary search, and we find the root cause, and we can automatically roll back the root cause. This is very important, but we can't do it, because if some of these tests are flaky, then I don't believe nothing, right? And this is a huge problem. The way we deal with it, we have a couple of deflaking strategies. It's something that gets more and more investment as time goes by, and I'm very happy for it. I was in another testing conference about 3 years ago, and I think almost all the presentation were talking about flakiness. So people really take flakiness seriously today. What we do is first give the developer the option to tag a test as flaky. So the first thing I do when I found out a test is flaky is just to tell the continuous build system, hey, this test is flaky. In response, the continuous build system will retry this test a number of more times in case it failed, right? So the default is 3, and the idea is to say, if I run this test 3 times and it succeeded in one of them, then the happy scenario got executed and I'm safe. If it failed, nevertheless, I don't know nothing, because it can be a false negative. So this is the most basic technique. Another thing we do is that we automatically have a system to calculate what we call flake probability of each test, which means that our continuous build system will invoke any failure again under the same condition. If it will pass in the second attempt, it will mark this invocation as flaky. And then over the history, the system will take the number of flakes, divide it with the number of overall passes, and we can see the historical flake level of a test. So a test that is 0% flaky means that it always reliably returns the true result. A test that is have 50% flake probability, it means that it's like flipping a coin, okay? It doesn't mean anything, like you better not run it. And then what we do, we use this flake probability to do interesting stuff. For example, each project can configure the threshold of flakiness that is willing to take in. So for example, in my project, we say that if a test is above 10% flaky, we will just quarantine it, mean that it will still be run, but in a different queue, and it will never block a developer from checking in, okay? And the system will also open a bug saying, hey, this test just the flake probability of this test just went up from 8% to 12%. This test was quarantined, and the system will open the bug with all the data, and the developer will know that now this test didn't behave so well, so someone have to take care for it. Another thing we do is we track changes in the flakiness level, because sometimes usually when we have a test which is 2% or 3% flaky, we say it's okay, because there is still a good chance, a very good chance statistically, that if I will run it 3 times, it will help me. But if this test is 20% flaky, it won't be as such, and someone need to deal with it. So this is a different thing. And I heard that in this conference I was back ago, I heard an interesting talk by Facebook saying that they do it exactly the other way around. Each new test that gets written is by default not being run as part of the pre-check-in workflow until it is proven to be stable. So this is another interesting approach to think about. Yeah, I think that's it. Thank you. Yeah.
So the flakiness, it gets tagged as flaky if it fits this particular criteria, that if it fails, then it's running in the background, and it only is considered flaky if it gets a different result running in the background?
So there are 2 different things. Maybe I went too quickly through this. First, as a developer, you can say, I suspect or I know this test is flaky, so you manually tag it as flaky. As a response, the continuous build system will retry it up to a certain time. Another thing is that flakiness can be discovered automatically by the system.
It's interesting. I guess my worry would be that if a test heroically uncovered a bug as a result of failing, would it have a risk of being marked as flaky and then that sort of being counted against it in the future stability?
This is problematic as well.
Right.
Yeah.
I mean, it's pretty rare that that would happen, that a test would actually uncover a bug. But
exactly.
Yeah.
And we tend to like ignore the happy scenario. Obviously, disaster can happen there as well. Like you can have a passing test at hiding a bug, but we tend to think less about this side. Anyway, yeah, go ahead.
What are the time boundaries between the test sizes, at least? Like you said, some milliseconds it's small, but how many milliseconds is medium?
Yeah, so the formal definition is that the small test must not never run more than 1 second. And I think a large test is something that takes more than 2 minutes, and anything else would be in the middle. They introduced a new definition that called enormous test, because sometimes we have, like, for example, you don't have a choice. You want to do a load against the system, and you need it to run like for 2 hours straight, and you need to think about it differently. There is, by the way, there is great blog post in Google testing blog about everything I talked about today. So if you, for example, search for test sizes, Google testing blog, or test size, or Google monolithic code repository, you will find good reads about this. Go ahead. Okay.
Hello. It's not much of a question, but I kind of want to clear out something. I have a problem with the term flakiness, because in my experience, if something is failing from one run to another, there are two options. One, the test is problematic. It doesn't have the same behavior throughout the numerous runs. Or two, the system under test is failing from different situations.
Yeah.
So to me, marking a test Flaky and not including them in a run or not investigating them in every possible way, I think it kind of covers the problem which is causing that flakiness. So how do you handle that? I mean, how much time do you spend on trying to figure out which is the problematic part, the test itself or the system under test? Thank you.
This is a very, very, very good point. I think first of all, there are multiple reasons for flakiness. So you made a high-level division between the problem is on the test side or the problem is on the system side, but even though there can be different reasons. Regardless of that, the point I want to make is that I don't care, like, as a first step, I don't care why the test is flaky. If the test is flaky, it doesn't serve me. Okay, this is the first, whether it's a test issue or a system issue, if I need to be able to trust my test. I need to know that if the test is passing, the scenario is successful, and if the test is failing, there is a bug. Anything else will just make damage. Now, you are right that the problem can be in both sides of the equation, and that definitely happens. The way I tend to think about it is that usually if you make sure that your test environment is hermetic, and the definition of hermetic is that the entire stack that need to be run can run on a single machine without connectivity, then it will usually, not always, but it will usually dictate determinism and stableness. So, because what usually happens, usually you have a test, and the test talks with a server that runs on a different machine, and sometime it will take the server 1 second to render the page, and sometime it will take 30 seconds to render the page because it was very busy, and Selenium will time out, right? But if I make sure that each scenario is executed locally on the same machine hermetically, then the condition should be exactly the same, at least theoretically, in each invocation, and the behavior will be the same. Now, I know this is not always easy to build such an environment, but I strongly encourage you to think about external dependencies that your test may have. And if you think about it, you will come to realize that a test that have external dependency is by definition not 100% stable, and we want to have as less as possible of those. Yeah.
Hello. Can you tell me, please, what is the main reason of flakiness in a Google? And it's interesting what is the amount of big, small, and middle tests in a Google in percentage.
I didn't get the second part of the question.
What is the amount of big, small, and middle tests in the Google?
So there are different reasons for flakiness. I think the most common root cause will be what we refer to as race condition. So if we have a process that runs asynchronously, okay, think about a browser that does the rendering and also issues cause in the background some AJAX call, okay? So it will never be deterministic what will happen before. Think about your browser that will issue 2 JavaScript AJAX calls in parallel, and when it gets a result, it renders a different part of the screen. So if it issues the calls on the same time, it's very hard to predict which of them will come back first. And this will heavily influence on the rendering process and how your browser looks. So if, for example, in such a scenario, you take a screenshot at a certain point in time, and you want to compare the screenshot to a different screenshot, then this test will very likely to fail. I think that, yeah, so I would say that asynchronously nature of processes is the main root cause. I think that another word which is very challenging is rendering itself, because especially in the world of visual testing, I don't know how much you rely on visual diffing tests as opposed to tests that rely on functional assertion, but when you start to rely on visual tests, then the browser have many undeterministic browser or any rendering technology have undeterministic properties. So it can sometimes say, I need to render this font in this color, and in order to give you a perception that is done very fast, it will compensate by, for example, changing 1 pixel from red to purple, because it will happen faster. You wouldn't notice it, because a human eye can't notice it. But when you do a pixel by pixel comparison, it will sometimes fail and sometimes succeed. So rendering, animation, everything with regards to visualization is hard. Anything else? Okay, thank you.